Generic data types. We can use generics to create definitions for items like function signatures or structs, which we can then use with many different concrete data types. Let's first look at how to define functions, structs, enums, and methods using generics. Then we'll discuss how generics affect code performance. That'll be good to know. I haven't heard a word in this book so far about how generics affect code performance. I'm looking forward to that. That could be interesting. In function definitions, when defining a function that uses generics, we place the generics in the signature of the function where we would usually specify the data types of the parameters and return value. Doing so makes our code more flexible and provides more functionality to callers of our function while preventing code duplication. Continuing with our largest function, listing 10.4 shows two functions that both find the largest value in a slice. So they duplicated the code for char. Here's what we have for the integer. Here's what we have for char. The only difference between the two is the data type that is here and the one that is returned. The reason for that is chars are under the hood integers. I think they're I8s, right? Could be wrong, but there's something along those lines. And then they rewrote the main function to incorporate chars. I think I can skip this. We pretty much have that. The largest underscore I32 function is the one we extracted in listing 10-3 that finds the largest I32 in a slice. The largest char function finds the largest char in a slice. The function bodies have the same code. So let's eliminate the duplication by introducing a generic type parameter in a single function. To parameterize the types in the new functions we will define, we need to name the type parameter, just as we do for the value parameters to a function. You can use any identifier as a type parameter name, but we'll use T because by convention, parameter names in Rust are short, often just a letter. And Rust type naming convention is camel case, short for type. T is the default choice for most Rust programmers. Okay, we'll use T. T for type. When we use a parameter in the body of the function, we have to declare the parameter name in the signature so the compiler knows what that name means. Similarly, when we use a type parameter name in a function signature, we have to declare the type parameter name before we use it. To define a generic largest function, place type name declarations inside angle brackets, these things, between the name of the function and the parameter list, like this. Oh, that's actually kind of ugly. Okay, so what they're saying here is that if we want to define a generic function, this is the syntax we have to use. After the function name, we have to put the generic, which is this thing, in angle brackets, T for type, and then the brackets defining the generic. And then we can say what we normally do. We have our list for the parameters being passed in, and this is going to be a pointer to a slice of type T. And it's going to return type T. So that makes sense. Okay. We read this definition as the function largest is generic over some type T. This function has one parameter named list, which is a slice of values of type T. The largest function will return a value of the same type T. Listing 10-5 shows the combined largest function definitions using the generic data types in its signature. The listing also shows how we can call the function with either a slice of I32 values or char values. Note that this code won't compile yet, but we'll fix that later in this chapter. Yeah, let's see what the error is. They have an example down there, but we can start writing this out. So they changed largest, they made it generic, T, and this is gonna be T, and guess what, you're gonna be T. And then you should work. Nothing else changed, right? List cannot be moved. Ooh, I see. There's an area there. And then this is going to be changed to, it's not no longer a number list. Let's make that a chart list. They changed that in the last example. We didn't copy that over. And give it some chars. They have a Y. I thought it was YMCA for a second. Nope. YM. I'll make mine YMCA. C. A. Should Y be the largest? I think Y is the largest in that set, so it doesn't really matter. Okay, cool. That's it. That should work. And let's see what error we get. Ooh. Binary operation greater than cannot be applied to type T. I see. So seemingly what they're telling us here is that think of all the different types in Rust, right? There exists a type that you cannot apply binary operations to. And because that type exists, our function is wrong. And Rust says no. T might need a bound for the standard library compare partial order. So T might need to be restricted or have seemingly this trait. I'm guessing it's a trait. See what they say. If we compile this, we get this error. Saw it. Partial order. Missing. Yep. Missing for T. The note mentions standard library compare partial order, which is a trait. We'll talk about traits in the next section. For now, this error states that the body of largest won't work for all possible types that T could be. Because we want to compare values of type T in the body, we can only use types whose values can be ordered. To enable comparisons, the standard library has the standard library compare partial order trait that you can implement on types. See Appendix C for more details about this trait. You'll learn how to specify that a generic type has a particular trait in the traits as parameter section. But let's first explore other ways of using generic type parameters. So what they're telling us here is that we're not going to fix it right now. They're going to teach us this later, but for now they want us to learn how to write the definitions of generics, functions, and other functionalities. That is annoying. Sorry code, you are broken. You will remain that way. So let's talk about structs and struct definitions. We can also define structs to use generic type parameters in one or more fields using the less than, greater than, like the angle bracket syntax. And listing 10-6 shows how to define a point struct to hold x and y coordinate values for any type. All right, we can find this struct. Let's see what they want us to learn. We have a struct, right? We'll call this struct point. It is a Cartesian coordinate plane, which is taking just x and y. There's no z-axis. All right, has type T, right? Well, a generic T. X is going to be of whatever T is, and Y is going to be whatever T is. And then in our main, we're going to say let integer equal not positive point x5 y 10. Have an M there instead of a comma. Bam. And then we're going to do the same thing for a float. Let float equal point. That doesn't need to have a space. 1.0 for x. 1.0 for x. And then y is going to be 4.0. So they're just demonstrating that with this syntax, we can pass in integers, so we can pass in floats, and we only had one struct definition here. Okay, interesting. Does it compile? It compiled. Wait, I have a warning that it's not being used. But it compiled. This worked. Noted. And let's see what they have to say. The syntax for using generics in struct definitions is similar to that used in function definitions. First, we declare the name of the type parameter inside angle brackets just after the name of the struct. So name of the struct, and right after that, name of the type parameter, which is T for type. And here are the angle brackets that is inside. Then we can use the generic type in the struct definition where we would otherwise specify concrete data types. So T, since it was declared here, can now be used here and here. Note that because we've used only one generic type to define point T, this definition says that the point T struct is generic over some type T, and the fields X and Y are both that same type, whatever that type may be. If we want to create an instance of point T that has values of different types, as in listing 10-7, our code won't compile. I see. So in this example, we have 5 and 4, 4.0. They're mixing an integer with a float, but an integer, which is probably I32, and a float, which I believe is like F32, quite possibly, are different concrete types. And based on our struct definition, we only have one concrete type. So since these are different, they will not compile. Or this won't compile. And here's the error. Expected integral variable found point. Oh, expected integral? What? I guess integral is another word for integer? Maybe. Because here it says expected type integer, return type float. Okay. Moving on. To define a point struct where X and Y are both generics, but could have different types, we can use multiple generic type parameters. For example, in listing 10-8, we can change the definition of point to be generic over type T and U, where X is of type T and Y is of type U. And here's that example. Pretty straightforward. Point T, comma U, two generic parameter types. X is going to be of type T, Y is going to be of type U, and then we have two different types here. What I am curious about is, no, it looks like if they are the same type, it still works. So here we have integer and integer. This worked. We have float, this worked, and we have integer and float, that worked. Okay, they can be different types or they can be the same type. Doesn't really matter. Got it. Now all of the instances of point shown are allowed. You can use as many generic type parameters in a definition as you want, but using more than a few makes your code hard to read. When you need lots of generic types in your code, it could indicate that your code needs restructuring into smaller pieces. That makes sense. Alright, enums. Can we do the same thing with enums? As we did with structs, we can define enums to hold generic data types in their variants. Let's take a look at the option enum that the standard library provides, which we used in chapter 6. We have enum option T defined just like we did everything else, some T, and then we have none. That works. This definition should now make more sense to you. As you can see, option T is an enum that is generic over type T and has two variants, some which holds a value of type T and none, and a none variant that doesn't hold any value. By using the option T enum, we can express the abstract concept of having an optional value, and because option T is generic, we can use this abstraction no matter what the type of the optional value is. makes sense. What they're saying here is that because it's generic, we can write this one thing and use it for any concrete type. Yeah, it makes sense. Enums can use multiple generic types as well. The definition of the result enum that was used in chapter 9 is one example. Okay, so this is an enum of one generic type, just has a T. Result is an example where they're using multiple generic types. We have T and E. E seemingly for error, T for type. Where OK returns T and error returns E. The result enum is generic over two types, T and E, and has two variants, OK, which holds a value of type T, and error, which holds a value of type E. This definition makes it convenient to use the result enum anywhere we have an operation that might succeed, return of a value of some type T, or fail, return an error of type E. In fact, this is what we used to open a file in listing 9-3, where T was filled in with the type standard library, file system, file, while the file was opened successfully, and E was filled with a type standard library, IO, error, when there were problems opening the file. You can recognize situations in your code with multiple struct or enum definitions that differ only in the types of values they hold. You can avoid duplication by using generic types instead in method definitions. Okay? We can implement methods on structs and enums as we did in chapter 5 and use a generic type in the definition too. Listing 10-9 shows that the point struct we defined in listing 10-6 with a method name X implemented on it. What? Really? Hold on. Oh, they really named the method X. Why would you name a method X? What does X do? I see. X is a getter. Makes sense. Okay. So what they did is they have our struct, our point has generic over some type T. We have our X and Y, which is of type T. And then we're defining a, let's just do one. We're defining a variable. Let's call it P because that's what they call it there. They gave it 5 and 10. This has 5 and 10. We now need to be able to access the values of X and Y because we currently can't do that because these are private. So we create a getter method. And this getter method is going to get the value of X. And we're going to call this method X. Not the greatest name, but I guess it works. So we're creating this method, which is generic over some type T. And we put the struct name like we would normally do, which is over some type T. And function X, which has a pointer to itself, it's going to return a pointer to type T. And the only thing it's going to access is self.x. And now we're going to demonstrate that we can access it by printing it out. Print line p.x is equal, let me write that correctly, to p.x. And we call it because it is a method. And this should work. p.x is equal to 5. That is correct. We have created a getter using generics. Here we define a method named X on point struct that returns a reference to the data in the field X. Note that we have to declare T just after implement. So right here, T is being declared right after implement, so that we can use to specify that we're implementing methods on the type point of some generic T. Okay? By declaring T as a generic type after implement, Rust can identify that the type in the angle brackets in point is a generic type rather than a concrete type. So in implementing methods, this has to be here for generics. it allows Rust to know that we're using generics. We could, for example, implement methods only on point float F32 instances rather than on point on some generic T instances with any generic type. So when listing 10-10, which is down here, we use the concrete type F32, meaning that we don't declare any types after implement. So let's test that out, because we can have, if I remember correctly, we can have as many implement blocks as we like. I'm just curious. Point, make this F32, right? And this is distance from origin. That's what they wrote here. Okay. Let me write function first. Function distance from origin. We have our pointer to self, allows us access to our self, x and y. We're returning an F32, and then we're seemingly doing some math. Self dot x dot power I. Okay. Plus self dot y dot power I. It should be about the same. I probably stands for integer, so taking powers of integers. Dot square root, and that's going to be returned. I'm just tempted to see if this actually works, because if this works, that means that we can have generics, and then for specific types where we want to do something different for, let's say, integers opposed to floats, or strings opposed to integers, we can specifically define that on the struct. Like, these are our exception cases. Do this for this type. And let's see if this works. So I would just declare another one just to be safe, I guess. Let's call it P2 equals point. We're going to have x be 2.3, 2.5, and y be 2.5. And do function P2 is doing this over distance. Why is it not popping up? Distance from origin. So it did pop up eventually. That's what I'm using. And see what happens. And that worked. Okay. So this is defined only for this type. So if you were to change this to P, which has integers in it, this should not work. Understood. Because this is not defined for the generic case. It's only defined for floats. That is interesting. Being able to mix that is kind of crazy. So let's see what they said. This code means that the type .f32 will have a method named distance from origin, and other instances of .t where t is not of type f32 will not have this method defined. The method measures how far our point is from the point at coordinates 0, 0, and uses mathematical operations that are available only for floating point types, which we verified. Generic type parameters in a struct definition aren't always the same as those you use in that struct's method signature. For example, enlisting 10-11 defines the method mixup on the point UT struct from listing 10-8. The method takes another point as a parameter, which might have different types from the self point we're calling mixup on. The method creates a new point instance with the x value from self that point of type t and the y value from the passed-in point of type W. That sounds a little confusing. Let's see what they wrote here. So we have our struct point, which takes in, this is over two different types, type T and type U. X is going to be a type T, Y is going to be a type U. We have the implementation of our method, mix-up, what they were talking about up there, which is going to be a generic method, a method that is implemented on the generic type of this function. And mix-up, which is operating over different generics, V and W, has self, so has access to point, and other, which is going to be another point of those two different types, IC, and it's going to return a point of type T and W. T being of the first one, so X is going to remain the same, but Y is going to change because Y is going to be of this type. So we're creating a new instance of point, which is going to be over these two types, X, which remains the same, and other Y, which is of this W type, and that's going to be returned. That makes sense. It's confusing to read up here, just because everything's being mixed around, but that makes sense. So let's look at it in this scenario. We have P1, X is an integer, 5, P2, which is going to be the other, Y, C. So P3 is going to be of X, 5, and of Y, C. Yeah, that makes sense. I'm not going to write that out. That would take a while to write. But that makes sense. Let's see if I can read it. In main, we define a point that has an I32 for X with value 5 and a float F64 for Y that has the value 10.4. The P2 variable is a point struct that has a string slice for X with value hello and a char for Y with value C. Calling mixup on P1 with the argument P2 gives us P3, which will have an I32 for X because X came from P1. The P3 variable will have a char for Y because Y came from P2. The print macro will call P3.x equal 5, C, which we already described up here. They're just putting into words what this is actually going to do. The purpose of this example is to demonstrate a situation in which some generic parameters are declared with implementation and some are declared with the method definition. Here, the generic parameters T and U are declared after implement because they go with the struct definition. The generic parameters V and W are declared after function mixup because they are only relevant to the method. So the point of this example was to show us how to mix generic method. The point of this example was to show us how to mix writing an implementation block with the user generics and mixing that with function definitions that use other generics. So we have these generics that apply to the struct and these generics that apply to something that was passed in. That was the point of the example. Okay, point learned. Performance of code using generics. You might be wondering whether there is a runtime cost when you're using generic type parameters. The good news is that Rust implements generics in such a way that your code doesn't run any slower using generic types than it would with concrete types. Rust accomplishes this by performing monomorphization of the code that is using generics at compile time. Monomorphization is the process of turning generic code into specific code by filling in the concrete types that are used when compiled. I see. So basically what they're saying here is that there is no cost to using generics because at runtime, Rust is going to write out all of the specific concrete types that this generic is being applied against. It's going to write all those functions out individually and you're going to have them. So it's just saving you the time of writing it. It's writing it for you. And then you're using that, at least under the hood. In this process, the compiler does the opposite of the steps we use to create the generic functions in listing 10.5. The compiler looks at all the places where generic code is called and generates code for the concrete types the generic code is called with. Let's look at how this works with an example that uses the standard library's option enum. So here we have sum5, sum 5.0. When Rust compiles this code, it performs monomorphization. During that process, the compiler reads the values that have been used in option T instances and identifies two kinds of options. One is I32 and the other is F64. As such, it expands the generic definition of option T into option I32 and option F64, thereby replacing the generic definition with specific ones. And they have an example of that down here. The monomorphized version of the code looks like the following. The generic option T is replaced with the specific definitions created by the compiler. I32, 64, yeah, that makes sense. Because Rust compiles generic code into code that specifies the type in each instance, we pay no runtime cost for using generics. When the code runs, it performs just as it would if we had duplicated each definition by hand. The process of monomorphization makes Rust generics extremely efficient at runtime. And that is the end of this section, and they didn't even put a summary or anything or like a segue to the next one. That's awkward. They usually do that. Oh well, yeah, I'm gonna start on the next video soon, and hopefully this was useful. I learned a lot about generics and how to write them. Peace.